Coriolis is going to start to change, isn't it? And you would expect it's not like all of a sudden it went through the toll booth and it had, but it's going to be a gradual change, and you're going to start to see the storm die out. Most storms don't cross the equator because of Coriolis. They tend to veer away. Okay? If we go back to that, the storm tracks. Notice the storm tracks, they don't look like they cross the equator, do they? They veer away from the equator. And that's because of the Coriolis effect that takes them off. So, yeah, but good question. And notice how, as this air comes out of the top of the hurricane, look what the direction of the air there. It changes direction, doesn't it? Because now it's not being fed by the air coming in laterally into the low pressure, but now it's above all of that. And now Coriolis swoops it around just like it should. So it's out of the storm system. So what's driving this? What's making this happen? Well, remember we talked about this idea that as air lifts, it cools and it can't hold all its moisture. It has to start coming out. When that moisture is in the air, it's in the form of vapor, isn't it? It's water vapor. But when it starts coming out of the air, it has to go through a phase change to become liquid water. And when it does that, it gives off energy. It gives off 540 calories per gram of energy. That's a lot of energy. That's what drives the system. That energy now gets converted into motion, i.e. wind. So the simple idea of all this hot, moist air lifting, cooling, hitting its dew point, having that energy come out of the system as we go through the phase change from vapor to liquid, that just keeps feeding it. The more I keep pumping that hot, moist air up there, and that energy keeps coming out of the system, this hurricane is just going to keep growing and growing and getting bigger and bigger. So the only way I'm going to kill a hurricane is to take away its fuel, right?
Yeah.
Okay. How much latent heat is given off during the phase change when water vapor becomes liquid water? Just told. Got everybody? A couple more. That's all it wants to answer? Okay. That's it.
Keep going.
We're turning it off.
No, don't do it.
No, waited too long.
You didn't know it could tell us.
There you go. Okay.
That's what I'm talking about.
All right. Well, let's look at C first of all. Heat is used up, not given off. No. Heat is given up. We'd use up heat if we were taking water and boiling it to make it into vapor, right? That would take heat. We'd have to put heat into the system to do that. But I'm taking water vapor and condensing it back down into liquid. That's giving off heat. Just the opposite. So, C's not it. 80 calories actually would be the change in phase from liquid water, freezing it into ice. There, all I'm doing is I'm rearranging some bonds between the molecules. But between liquid water and vapor, I've had to break those bonds to liberate those little water molecules to let them become free-range molecules, right? So now, as I remake those bonds, the energy is given off in the process, and everything's condensing into liquid water. And I'm taking a heck of a lot more energy to make bonds than I am to just stretch them around a little bit. So 540 calories a gram is what it's going to do at that, what we call latent heat level. The reason it's called latent is because what's happening there is all the energy is going into the change of the bonds between the molecules. There is no change in temperature. All this energy, all this heat is going in or out of the system, and the temperature isn't changing it. It's all getting used up in remaking or breaking bonds. So it's called the latent leg of the system. That's a lot of energy. That's going to drive the hurricane. Here's Hurricane Kate. When it came through in November of 1985, it was the biggest hurricane on record, and did about $1 billion in damage and caused 7 deaths down in the Keys. This is a street, and you can see it's underwater. And all of this water is not there because of the rain coming out of the system. It's there because of the wind, and you can see that's pretty substantial. The wind is pushing the water out of the Gulf of Mexico in over the land, and this storm surge is what's flooding the area. It's not the precipitation coming out of the sky. Here's Hurricane George. This came across in 1998, and you can see the hurricane here. There's the eye, nicely developed eye there. You can see the guy spinning counterclockwise here, northern hemisphere, right? And this is a day-by-day track of where it went. Well developed here. Look at how well the eye is developed here, not in here, but then look what happens here. It comes in over the islands, over Haiti, the Dominican Republic, Cuba, and look what happens to the storm's organization. It kind of starts falling apart. You don't see the nicely developed eye anymore. What's happened is I've got all these islands. That landmass is cutting off area that could be devoted to fuel supply. In other words, nice, warm, moist water. So as it comes in over the land, it's losing its fuel supply. It's becoming disorganized and dying down. But look what happens. It gets right off of the tip of Cuba, gets back into the warm water of the Gulf of Mexico, and immediately, look what happens. You can see the hurricane eye develop nicely. It then crosses into the United States, and it doesn't get to the north side of Mississippi, Alabama. The moisture's cut off. It's done. That's it.
So the water's going to be warmer than the land's going to be then?
It's not so much that it's that much warmer, it's that much wetter. It's that moist water. Remember, we're making that change from water vapor to liquid water. So we've got to get that water vapor up in the sky. And you're going to do that over warm water. Over warm land, it's still going to be warm, but where's the water vapor coming from? A little maybe, but not much. And that's what happens. You get in over the land, you basically cut off that supply of moisture, you stop the hurricane. It cuts off the fuel, there's no more latent heat leg change of 540 calories to drive the system, and it just falls apart. So the tracks are kind of there because of Coriolis. Coriolis kind of keeps them moving away from the equator, and land shuts them off. Now, if you're going to get hit by a hurricane, and you have your choice as to which side of the hurricane is going to hit you, you always want to take the soft side. So what do I mean by that? Well, remember 2 things about the hurricane. It's rotating, right? So it's a big rotating mass of cloud and wind and water. Plus, it's moving along. So if I combine those 2 things, here we've got Florida down here, Georgia. So here's the east coast of the U.S., North Carolina's up in here, here's Cape Hatteras right there. And I've got this lovely hurricane just about ready for the eye to hit the coastline. And as a good hurricane in the northern hemisphere, it's rotating counterclockwise, just like it should. Okay, overall, the hurricane is moving 50 kilometers an hour toward the northwest. So this eye is moving in that direction, right, the whole thing. Now, it's also rotating. So over here, basically the wind speed is 170 miles or kilometers per hour. So if I add the rotational speed of the cloud with the overall movement of the storm, The net speed over here is 225 kilometers an hour. But over here, because of the rotation, now the rotation is going in the opposite direction. The storm's still moving toward the northwest, but now the net speed is 125 kilometers an hour. I've subtracted because the wind is moving in the opposite direction that the storm's moving. There's the soft side. I'd rather get hit by 125 km/h winds rather than 225. What a difference. So, soft side of the hurricane, hard side of the hurricane.
Is the soft side always on the left like that then, since the way it rotates?
Yeah, it's always going to rotate counterclockwise, so it's always going to be that left side. Just the opposite in the southern hemisphere, right?
Right.
Yeah. Okay. So the storm surge is kind of interesting. If I look at one of these big storms coming through, it's a lifting mass of low pressure air, right? It's like running the vacuum cleaner hose over the surface of the ocean. And it's going to actually lift the surface of the ocean. And it can lift the surface of the ocean as much as about 3 feet. That's pretty significant. The other thing that it's doing is it's pushing the water out in front of it. And as it does that, it's just making a big wave out in front of the storm as it moves along. There's the storm surge. That's the one that's going to do a lot of the damage. As that storm surge comes through, it's like just one big wave. These can be pretty significant. The storm surge that hit Galveston in 1901 was estimated to be 17 feet tall. That's like the middle of the second story, most of the houses in Galveston. So just that one storm surge was pretty destructive. And this is what it looked like. It came through, took out even substantial brick buildings. You can see what it did in the dock area. It took this big sailing ship and threw it up on the docks. Just wiped out all of the basic stick frame type of housing. And it promoted building of the seawall that wasn't there at the time. It now has a 17-foot seawall that's partly buried in the sea. But this still ranks as the #1 natural disaster in the United States. It killed somewhere between 6,000 to 8,000 people. And they just didn't have good census numbers back then. There was a lot of traffic in and out, so they really didn't have a good count, but they know it was at least a minimum of 6,000. And for the next 3 months, as you sailed past Galveston, there was a horrible smell. And you could see bonfires on the beaches as they burned the bodies. It was an incredible disaster. Okay, so hurricanes are something that you kind of need to take keep in mind. We don't see too many of them up here. We're pretty fortunate in this part of the country. Most of the ones you're going to see here are going to tend to be early spring or fall, because they're going to be extratropical hurricanes. We're not going to see tropical hurricanes get this far north. We might see some extra rain, but we're not going to see a big tropical hurricane this far north. By the time it comes over the land, it's going to die out long before it gets up here. Most it's going to do is influence the weather a little bit and put a little rain to it. So we're going to see extratropical hurricanes here. So what is the wind speed necessary for it to be classified as a hurricane? When does it become a hurricane? 35? 75, yeah. 75 miles an hour is hurricane speed. And they have a number of different classifications. But, oftentimes in the spring and the fall, we will see 55 to 75 mile an hour wind gusts. So we're kind of getting there. But it's the sustained speed that's what they're looking at. So you'll get a taste of it here and there. Okay. Any questions about hurricanes? Okay. I want to keep on going. We've got about another 7-8 minutes, but I don't want to just blow it off because we're a little behind. But let's change topics now. I want to kind of introduce and get started on rivers. And rivers are the way we distribute a lot of our surface water around planet Earth. You know, you think in terms of the Mississippi River. Here's a huge river with a lot of water, but if you look at it, it's a very small percentage of the surface water on Earth. Most of the water on Earth is really out in the ocean. If we look at it, the oceans contain about 97.2% of the water on the face of Earth. And that means of the 2.8% that's left, that's going to be fresh water. All this ocean water is going to be salt water. So we've got a very small amount that is going to be water that we can use, that's going to be fresh, usable water. And of that, 2.8%, 2.15% of that is tied up as ice in glaciers. So right away, most of the fresh water we've got on Earth, we can't even use. And out of that, then, about a little more than another 0.5% is groundwater, and that's what we pump for use. And streams, and lakes, and freshwater lakes, and atmosphere all account for just this little sliver here. Basically, if you look at stream channels, 0.0001%, not a whole lot. The point I'm making here is there isn't a lot of fresh water on Earth. Most of it that we do have is tied up as glaciers, and the little bit that we have left in groundwater, streams, lakes, is pretty insignificant compared to the water that Earth does have. That's the water we depend on. So we've got to figure out ways to take care of that water because, yeah, we need it. And if we have to let Mother Nature recycle it to clean it up, most of that water, well, for instance, glaciers. Most glaciers are going to tie up fresh water for about 1,000 years. To get groundwater through the system, back to the ocean, back through vapor, rainfall, back into the land system, we're talking decades, tens of years, at least, if not hundreds. To get it as surface runoff, it might be as small as a few months to a few years. But that's, as you can see here, an incredibly small amount of the total. So we've got to take care of what we've got. Groundwater and surface water, fresh water, is going to be more and more and more critical as the population continues to expand. This is going to be kind of one of the big limiting factors on our growth as a species.
Why can't we make ocean water?
Make it potable, yeah. Desalinize ocean water, we can. In fact, that's where most of the Middle East gets its water with its population since the Second World War. The thing is, it's very expensive. Tampa, Florida, which is about halfway up the coast on the west coast of Florida, so it's on the Gulf of Mexico. They cannot meet their freshwater demand for water for the city. Haven't for decades. And they desalinize water. They also have some of the highest water bills in the United States. It costs money. You can do it, but be prepared. Now, we think in terms of the Mississippi River, this is a really big river. And for us it is, that's our biggest river. But on a worldwide basis, it ranks as number 7. It's not that big. If we think about it, most of these rivers that are bigger are places like Southeast Asia, South America, places that have a lot of rainfall, places that have monsoons. They're in the tropics and subtropics. Those are the areas. So here's the true and false before you all...
Getting crazy.
I know, you're all packing up, but there's 4 more minutes, guys. Okay, the largest body of fresh water on Earth is the Great Lakes, 4 of which border